Hi, everyone. It's my great pleasure to share with you some of our recent studies on flexible hybrid electronics, particularly targeting high fidelity and the large area sensing system. My name is Cheng. I'm with Hong Kong University of Science and Technology. The background photo is our campus. After the pandemic, I welcome you to visit us, a campus right next to the Pacific Ocean. A quick outline of my talk. I will very quickly go over the opportunities and challenges of flexible hybrid electronics, and then discuss the design automation issues, particularly compact modeling and the PDK development. And then I will quickly discuss the design of flexible electronics using Pseudo CMOS design styles and give two quick demonstrations. One is ultra thin and high quality skin sensor silicon interfacing, and the second one is robust sensing for large area sensor array. So let's look at today's wearable devices, which has been explosive. And the illustrated example here is for ECG monitoring. We have seen devices in different form factors, from bracelet to watch style to portable car styles to vest styles and to the popular patch style, which is like Band-Aid. Even with the Band-Aid format, you can see the contact still not ideal. There's significant air gap between skin and electrode. And I borrowed the figure from the 2013 advanced material paper illustrating that the thickness of the substrate for flexible electronics has to be ultra thin, in this case is 5 micron or even thinner, in order to get good conformability for the contact, which is highly essential for high signal quality. And any large L gap will introduce attenuations in both gain and the phase of the amplifier. Here, right-hand side is a very simple illustration that if there is no L gap, eliminate the middle part, then the gain and the phase will be close to ideal. But when the air gap increase, the degradation in post gain and the phases become very significant. So in the past 10 plus years, we have seen enormous progresses in flexible devices, which are flexible, thin, stretchable, conformable, transparent, and some are biocompatible, very lightweight, and increasingly for the sensor application, they must be highly cost effective. And I don't intend to give a comprehensive overview of the flexible thin-film transistor technology. I think for this audience, most of you are very familiar with this, but I like to highlight key attributes which are very important for the design of flexible electronics. One is the process temperature. I think being able to do that in the room temperature and low enough to fabricate the TFTs on flexible substrates is essential. And the feature size today, I think we have seen technology successfully reduce that to single digits, such as a 2 to 5 micron feature size. And the substrates can be on glasses, plastics, and increasingly even more innovative substrates. And one key problem for thin-film transistors are the monotype availability. Almost all thin-film transistors only have one type of stable devices, either N-type for amorphous silicon or metal oxide, or P-type for organic or common nanotube TFTs. In terms of supply voltage, we have seen tremendous reduction from 20 plus volts. Now today's common nanotube TFT with 2 volts supply voltages, which make it very compatible with the CMOS devices. Mobility, we have seen tremendous progress, but still in the low tens, which limited its applications for computing. Due to the low mobility, it's not suitable to do computing using flexible devices. So the ideal solution we'll call the flexible hybrid electronics. Sensors, which are flexible, built on top of flexible substrate, high conformability to, but then connected through printed interconnect, then connect them into high performance and low power silicon chips, all the compute intensive, memory intensive part into the SoC. So this part, the flexible electronics, also called skin electronics, skin sensor, will be based on flexible electronics. Then the printed interconnect eventually goes through the flexible to rigid interface to the SoC. Since you want to sense data, there are a lot of motion artifact in noise induced. So there is a need to build high gain amplifier directly into the large area sensor. The signal you can sense is still in the millivolt range. For example, the ECG signal is only about single-digit millivolts range. That signal, if you transmit through the printed interconnect, which give also at least millions millivolt noise, or even tens of millivolts noise due to motion running, then your signal will be completely lost. So you need to be able to amplify that signal and implement that amplifier into the flexible sensor. So what are the key challenges for flexible TFT circuit design? This slide summarizes the key problems. One is the material is still relatively unstable compared with silicon materials. There are two kinds of degradation. Chemical degradation, when the material is exposed to oxygen or water vapor, not necessarily a droplet. The other is the electrical degradation, that if you continue to run it, the stress will cause very significant electrical degradation to the material. Second thing is a process variation. Think about that you're going to fabricate transistor on a very flexible, stretchable substrate. So easily the geometry will shift in a non-trivial way. That will cause geometry variation, also result in threshold voltage change variation. And also from device to device, there's significant mismatches. The third is device limitation, and for flexible TFT, they usually only have a monotype, either P or N, depending on which technology you use, but you cannot use both to design your circuit. And another issue is the low mobility. But finally, there's little EDA tools, so no PDK support. No compact model for circuit simulation, reliability simulation, and the stretch simulation. So for the rest of the talk, I'm going to talk about some of the progress being made on design automation and on circuit design. So this slide summarizes our vision on the design infrastructure for flexible hybrid electronics. It's a joint project between HP, UCSB, Stanford, and Georgia Tech, along with several other CAD companies. We want to bring design environment, PDK, foundry, the design community all together. From the foundry part, silicon, of course, there are a huge number of foundries that they can provide the silicon chips, and there are foundry who can provide the thin silicon. And for flexible electronics, there are a wide range of foundries. So the first thing is we need to design a process development kit, PDK, to support the interface between design and the foundry. So this is not new for silicon, but we just really need to redo it for flexible electronics, creating the technology file, parameterize the cell, and compact model described in a Verilog A phone so that it can be used for standard EDA tool for simulation. And all this model must be enabled the simulation for the electrical aspect, mechanical aspect, and thermal simulation, and the electrical magnetics. But once you are able to develop PDK, describe all this in the technology file, then today's design environment that we're very familiar with, from Cadence, Synopsys, Mentors, those tools can directly take those specified file as input, then allow us to do integrated simulation, layout, and verification for flexible hybrid circuit, which include flexible part and the silicon part. And that then will be enable the designer to design sensors for medical fitness, industrial, military application, pretty much like what the silicon chip designer has been designing their chip today. So we drive this project by selecting the technology from Stanford, which Professor Zheng Anbao's group and for many years has been developing a common nanotube TFT technology, which can be manufactured on top of polymer flexible substrate and have a 2-layer of metal. If you're interested, you can take a look of our recent paper in Nature Communication. But we will be able to get a very high yield based on this CNT-based TFT. In order to design circuits, we need to also have some passive elements such as resistors, capacitors, also interconnect based on the CNT technology. So these are the cross view and top view. There have been a lot of experiment device manufacturing to ensure their high yield and repeatability. So with that background, the first task is to
develop PDK, which involve a number of tasks. One is develop compact models, which can be described in the Verilog A form to enable SPICE-like simulation. And also, we need to derive technology file, including design rule definition, device definition, and parasitic definition. For example, if you look at the TFT, all the geometry, what are the minimum width, height for each of the polygons, all fully specified. Develop accurate compact model and have all the device geometry rules and the parasitic well defined. Performing the layout design rule checking, LBS, parasitic extraction for post layout simulation all become straightforward process, which many of us are very familiar with that. So our focus for a period of 2 years has been highlighted boxes. For example, we start out develop compact model for common nanotube TFT through repeated experiment and measurement for verification of the model. So without getting into too much detail, I just show you the result that showed a very high accuracy or high match between the measurement data and the model. The detail of the model are described in IEEE Design Test magazine's paper, but we're not only being able to develop a unified model for all range of TFT devices, we further confirm that they be used to match organic TFT and oxide-based TFT. So regardless what kind of TFT flexible technology you use, this unified compact model can actually represent all ranges of flexible TFT devices. With the compact model, the next question is, can we develop standard cell for flexible TFT? Because if we can design inverter, then based on that, we can design all kinds of gate, flip-flop, building block. Then we have a cell library. But the problem is for combinable TFT, only P devices available. So we need to design inverter purely based on P TFT. We come up with a design style called Pseudo CMOS design, where instead of owning 2 transistors, we use 4 TFTs to design inverter. Like CMOS, that you want to have the output to be rail to rail. So when it go high, go to VDD. When it go low, go to ground. Therefore, you can cascade as many building blocks as possible to form a digital circuit. Therefore, in order to accomplish that, you need to have a level shifter as a first stage to support the main stage of your inverter. So left-hand side is the design of the PMOS based inverter. The detail described in our paper in transaction of electron devices. For other kind of flexible TFT, if there's only an NTFT available, then we also offer similar cell for the inverter. So the cell, instead of owning 2 voltage, VDD and ground, actually there's one more called VSS. So it's a 3 voltage level design, and it consists of a level shifter. Another very important characteristic needed for this design is the post-tuning capability. This VSS, if I apply different voltage, I can improve the performance dynamically. So left-hand side is the schematic of the inverter, and there's 3 voltage, VDD, ground, plus VSS. Assume VDD is 2 volt and ground is 0 volt. If you leave VSS as 0 volt, and we fabricate a large number of such inverters, you will find the transitions, switching voltage has wide variation, because all the TFT devices, of course, is far from ideal. The variation is significant. So if you leave that as a 0 volt, then even though it's a rail to rail, it's only 2 volt, but the transition range has variation of 0.5 volt, which is 25% of the entire rail. And also the gain is very limited, only 15 to 30. But for the exactly same device, if we apply instead of -1 volt to VSS, then the transition range will be tightened up, the variation reduced significantly from 0.5 to 0.3 volt. Not only that, the gain increase from this range to this range. If we further apply a higher voltage, -3 volt in VSS, variation is further reduced and the gain is further increased. There are 50% reduction on the variation and the 10 times gain of increase. To summarize, Pseudo CMOS design to address the monotype device limitation and address the problem caused by large process variation. And even though we worked on that many years ago, very few people was interested. But suddenly when flexible electronic design for larger scale design become of greater interest, suddenly everybody is using that for designing their flexible circuit. For example, this one is from iMac to design actually simple microprocessor using the Pseudo CMOS design style and also design a RFID. And this is a demonstration of an RFID. And whenever you need to have a inverter amplifier, they always use a Pseudo CMOS design style. Then we further design all kinds of cell libraries, NAND gates, ring oscillators, D flip-flops, and the 8-stage shift register. Take an 8-stage shift register example, which consists of 456 TFT. Imagine that you have to make them extremely robust based on very unreliable high variant devices. Being able to accomplish that to demonstrate a really working 8-stage shift register actually was considered a breakthrough. The speed is also a record. So to summarize, in terms of the transistor count of the working transistor on a single component, this was the performance of an inverter. For both metrics, we achieved 10x improvement compared with any other prior work. And then we conclude this is coming from two aspects. One is the CNT devices yield actually getting reasonably high. Second is the pseudo CMOS design being able to address the limitations. Third is because the PDK, the compact model, allow us to optimize the design, and all the combination from 3 angles leads to these results. So then with that, the next thing is we want to really demonstrate skin electronics. So one application is, can we implement this into a flexible skin electronics? And the schematic is for the electrode. We not only want to be able to make a good contact to the skin without air gap. Also, we want to implement an amplifier that to achieve high gain amplification to bring body signal, electrical signal from millivolt to volt, 3 order of magnitude magnification, that will 60 dB amplifier. After that, the rest I think is straightforward. Signal will be highly tolerant to the motion noise before reaching the CMOS part, which can do all kinds of signal processing, machine learning operation. This integrated amplifier implemented on a skin electronic, being able to get high gain is what we needed. Design schematic showing here, one of the key element is that it's tunable for the gain, which we call tunable gain amplifier. Here is the frequency responses, where you can see that applying different voltage at the tuning node, you will be able to shift the region of the high gain to a left or right, fall into the range that conform to the type of signal we want to measure. Typically, for most of body signal in the range of tens of kilohertz. These are the measurement results. We will be able to get some devices get a 60 dB gain at the 20 kilohertz range. And it's very small. It's 350 by 350 micron size, and fabricated in a very thin substrate, 2 micron thickness I mentioned earlier, that can be totally conformed to your skin. And it's very low power, ranging from only 100 microwatt to 500 microwatt. The last issue I want to discuss is large array of sensor. For example, this is a glove, and you can fabricate huge number sensors in an array structure. But the problem is the flexible electronics building on the flexible substrate today, the sensor yield is still relatively low. We cannot expect that everything work here 100%. How will we address this? This will use a system solution. You don't need to make every single sensor node here work. If some doesn't work because or the density of the sensor is relatively high, but the information like temperature or the pressure sensing using your palm or glove or ultrasound sensor, you don't really need to have every single sensor work. And this is confirmed by our analysis showing that biosensing signal are sparse. Pressure sensing, temperature sensing, or ultrasound sensing as example. In this case, we have sensor array of 100 by 33. If a sensor array like that, and you do DCT transformation to kind of find a coefficient. For pressure sensor, out of this 3,300 size array, only about 500 of them has a coefficient which is non-trivial. Majority of them, let's say the value of coefficient smaller than 10 to the minus 1. Only 1/6 of them for pressure sensor that is non-trivial. For temperature sensor, it's about 20%, 25%. And even for ultrasound sensor, the information is richer, about 50% are non-trivial. And this right-hand side basically saying the same thing. Only about 40-50% of the sensor node in the sensor array have a non-trivial DCT coefficient. So it's about 50% sparsity. Therefore, we can use so-called compressed sensing technology. The idea is you just sample a subset of nodes in the array and rely on that, send the signal to the silicon chip, which do the decoding. To do the compressed sensing encoding, the sensor is extremely simple. We call dump encoder, which basically is a simple sampler, sample a subset of data, and send a subset of data to the decoder side, which require very extensive decoding. But since in the silicon side, you can design complicated circuit. Therefore, we can do the error correction through compressed sensing, eliminate all the nodes which are too noisy or too much deviation from the rest of the neighbor, or even defective one. Design such a case, we use the glove example. Like say you have a large number of sensors in this artificial glove, which is totally conformed to your hand, your palm. But the dot here basically showing some of them are just not working. Since it's a large array, typically you need to have sampling circuitry. So we build a dump compressed sensing encoder and send that into the silicon chip, which we add a smart compressed sensing decoder. Since we sample only a subset of them, what the decoder receives for the sample data actually is relatively sparse and somewhat random. Then through compressed sensing decoding, you eventually can reconstruct with high fidelity. So even though the devices, each of the sensors is not as reliable, final temperature map or pressure map or ultrasound map will have a very high fidelity. The detail of the work is described in this. Instead of trying to sense every single element in the sensor array, which is active matrix, if it's n by n array, we only sense square root of n per column, and also only sense square root of n of n row. And how to sense it and how to design the peripheral circuit, which rely also on some shift register, which is shown here, are detailed in that paper. But I believe by now I have describe the background, how to build a sensor and how to build a digital circuit. So this can be implemented. Low thousand of TFT will be able to make such a sensor array plus peripheral circuits plus the shift register. I summarize here. I address the flexible hybrid circuit designs to start out as a design automation issues. Doing compact modeling for new flexible TFT is a foundational task. Based on that, we are able to build a design platform, flexible hybrid electronics PDK. And after we produce that PDA, actually Netflix has recommended it as a standard. Then I talk about flexible circuit design. I introduce CMOS design style, which fundamentally addressing the problem of bias variation as well as the monotype of transistor. And based on this design style, we have developed a wide range of cells and developed a cell library for CNT-based TFT. And based on them, the several flexible chips has been designed, which demonstrate improvement of performance by at least 10x. And finally, we gave a couple skin electronics demonstration. The first one is active electrode design, alleviating the noise in the skin sensor silicon interfacing, because the flexible part is so conformable to your skin. So there will be little impact due to the noise artifact. Being able to build the amplifier right next to the electrode, minimize the noise interference for the rest of the transmission to the silicon part. And finally, we introduce a compressed sensing-based encoder-decoder design to address the problem of any sensor array would inevitably have a yield, reliability, and the stability problem. Combining with the system solution of compressor sensing, then you still can build a highly reliable sensing system based on the large sensor array.
Before I conclude my talk, I would like to acknowledge my collaborators, Dr. Leilai Shao of UC Santa Barbara, my former PhD student, Dr. Jing Huang, researchers at HP Labs, now currently with Facebook, Professor Zhen Bao, and Dr. Ting Lei of Stanford University. Dr. Ting Lei now is with Beijing University. And finally, Professor Pan Yun, who is with Zhejiang University. Thank you so much for your attention.